Okay, so we've learned about this idea of a stress tensor. We're calling it tau. It has these components ij, and we've learned what the index notation means in terms of which component is pointing in which direction, and you're probably trying to remember your i's and the j's, which we defined in the previous lecture. But we made life a little bit easier by recognizing that at least in this class, where we're not interested in non-conservative body forces, that this tensor is symmetric. And so if this tensor is symmetric, then in fact you don't have to remember too much which one is which, because we'll find that tau ij is always equal to tau ji. And so which one is the one direction and the two direction doesn't matter so much in what we do going forward. What we do care about, however, is being able to come back to this idea of finding a traction vector. And so we'd like to find an expression for the force per unit area acting on a little element of area of size dA. The derivation of this is rather tedious and involves lots of geometry. It was first done by Cauchy, and so he used as an example thinking about forces on a little triangular element, like this, so for Cauchy. And he thought about forces acting on a little triangular element like this, and thought about all the different ways we can compile forces on that. And the nice thing about an element like this is I can change the orientation of it. It's got a magnitude dA and a normal vector n, and I'm just going to give you the result, and you can find derivations online if you're interested in it. But at the end of the day, the expression that we want is an expression for the force, F, and it's given in terms of the outward-facing normal n and our tensor tau as a dot product between the normal and the tensor. And so this is a dot product. That means that when we think about the number of free indices, the dot product removes two of them, and we end up with just one. So this is a force per unit area. So we've called this a traction vector, and so that's the best way of thinking about it. And if you're interested in the total force on an area dA, then the total force would be multiplying that by this, would give you the total force. If I write this out in component form, then we would have Ni, Ei would be how I would represent my unit vector. And I would be dotting this into tau. And let's write this out in component form. So in component form, we'll have a j and a k and two free base vectors. And so the dot product will operate on these two. And so this will give me delta ij. And this means that this is only non-zero when I is equal to j, so they're the same. So I can also write this out at the end of the day as equal to ni tau I k e k. So it's very clear that this is indeed a vector which has got a summation over I. Of these different components, and it's a vector that has base vectors, base indices k left over. So it's a vector. We can do an example of that, and so let's think about a very simple little example. Let's think about an example where let's take a little element of area and point it in a particular direction. So n is equal to, in this case, E2. And underneath here, we've got a material which has got a stress in it. And we're interested in finding all of the components of the stress that are acting on this little elemental area. So we can use this result right here. And we can say that the force is nothing but Ey, or E2 in this case. So E2 is the base vector, dotted into tau, and we'll use j and k, ej, ek. So if I do this operation, then I have to take the dot product of the base vector in the to direction and the j direction. So this will give me delta j2 times tau j k e k. And let's write that out, okay? So we can find that this Kronecker delta is only going to be non-zero when j is equal to 2. And so then we will have tau 2k e k. And again, that's going to be written for all of the different values of k. So we can write this out as tau 2 1 e1 plus tau 2 2 E2 plus tau 2 3 E3. And so it's very clear that this is indeed a vector force, and it's a vector force with components that are acting in this direction, tau 2 1, acting in this direction, tau 2 2, and also, of course, a third component acting in this direction, which is tau 2 3. And you can see that this keeps all of our sign convention consistent. The first index is always a 2, because this is a force acting on a surface with the normal in the 2 direction, and then the last component tells you in which direction the forces are acting. So this is going to be very, very useful as we go on. In fact, we can see one example of how this is going to be useful right now by using something that we've seen in the math review, which is called Gauss's theorem. So this is often also something that people would call the divergence theorem. And the idea is you might remember that it allows us to take an area integral of something and convert it into a volume integral, where we'll take a volume integral of the divergence of something. And so we can use that using this idea that we've developed here. And so we can substitute in here, for example, n dot tau. And we can say in words what this is. We know that n dot tau is the local force on every little point around here. So on every little element here, we have a way of evaluating the force per unit area acting at every single point on our surface. And that's what this gives us. So this is the total force acting on it. And so these are all of the surface forces. So this is an expression for the total surface forces acting on our volume. And all we have to do is we just have to take that using the divergence theorem, and so we can also express that in terms of the divergence of the stress. This quantity is sometimes a little scary to look at because this is the divergence of not a scalar or a vector, but it is the divergence of a stress. And so if we were to think about what these terms are, this would be to say take d by dxi of something with a unit operation EI dotted into tau jk ej ek, just as we had here. And so we'll put this in here. And this is going to be very useful as we go forward because it'll allow us to, sometimes it's easier to think about total forces acting on the surface. But another way of thinking about this is that it's equal to the divergence of the state of the stress inside our object integrated over the whole volume.